Solubility is also strongly related to compound type. First, let's talk a little about the process of dissolving. To dissolve, three things have to happen, and they often happen simultaneously. The solute-to-solute interactions have to be broken. This makes the solute let go of other solute particles. The solute needs to be distributed in the solvent. This gets them intermingled. And then the solvent-solvent interactions have to be successfully replaced with solute-to-solvent interactions so that the solute will stay intermingled in the solvent. In general, we sometimes say like dissolves like. What this means is that last important step where the solute and the solvent have to be able to set up successful interactions. They have to be like each other to do that. Polar substances can do this with other polar substances, and a solution will form. Nonpolar substances can do this with other nonpolar substances, and a solution will form. But polar substances and nonpolar substances cannot form successful solute-to-solvent interactions. We can extend this to include ionic compounds. It isn't exactly a case of like, but ionic compounds often do dissolve in ionizing solvents like water. So let's take a look at some examples of like dissolves like. And let's also look at what happens when you change the solvent, how much that will change the solubility. Because remember, changing the solvent is going to require different solute-solvent interactions to be able to take place.
Adding alcohol to the test tube on the left forms a homogeneous mixture because alcohol is soluble in water. Adding heptane to the test tube on the right forms a heterogeneous mixture because heptane is insoluble in water.
Nonpolar carbon tetrachloride is poured into a test tube. When the nonpolar colored solid is added, the solid dissolves in the carbon tetrachloride. When polar water is added to the test tube, it forms a layer on top of the carbon tetrachloride, since water is immiscible with and less dense than carbon tetrachloride. When nonpolar hexane is added to the test tube, it forms a layer on top of the water, since hexane is immiscible with and less dense than water. When the test tube is vigorously shaken, the two nonpolar liquids form a single layer at the bottom of the test tube, and the polar water layer sits above this layer. Ethanol is poured into a saturated calcium acetate solution. A precipitate rapidly forms as the solubility of the calcium acetate is reduced. Liquid is trapped in the network of solid calcium acetate, forming a gel. When ignited, the alcohol in the gel burns. Similar gels are used as a source of fuel in portable cooking stoves.
Let's talk about some common solvents for a moment. Water is a polar and ionizing solvent. It dissolves polar solutes and many ionics, or salts. But water's not the only solvent in town. Hydrocarbons, in general, are nonpolar solvents. Hydrocarbons contain only carbon and hydrogen. These are nonpolar, and they dissolve other nonpolar substances very well. So this also means that water and hydrocarbons are unlike each other. What if you wanted to get them to try to intermingle? Then you'd need an emulsifying agent. Emulsifying agents assist polar and nonpolar materials to suspend in each other longer and more completely than they would on their own. They still do not dissolve. A solution is not formed, but they intermingle longer than they would on their own. Soaps and other substances that have dual character are good emulsifiers. What emulsifying agents do is facilitate temporary mixing of unlike substances. Phospholipids can also be emulsifiers. Look for lecithin on packages, and consider the use of eggs, which contain lecithin, when cooking with water, oil, flour, and/or sugars. The lungs also make a surfactant, essentially an emulsifier, that helps oxygen reach the bloodstream through the lung lining. Premature babies do not make enough of this surfactant and can be helped with a synthetic version. So what are solutions? They're defined as homogeneous mixtures of two or more physically mixed components. Whatever component is present in the greatest quantity is called the solvent. All other components are solutes. The solute is distributed uniformly within the solvent. The solute is molecular or ionic in size. The solute will not settle out on standing, and the solute cannot be filtered out. All four of these characteristics are what it means to be a homogeneous mixture. We'll talk primarily about aqueous solutions. Water is an important solvent, and any solution where water is the solvent is called aqueous. NaClS stands for solid sodium chloride, but NaClAQ represents sodium chloride dissolved in water. We can do the same with table sugar. C12H22O11S is solid sucrose, whereas if you put an AQ on it, it's dissolved in water. So there's two words in this definition of a solution, homogeneous and mixture. Let me remind you of a couple of the features of a mixture. One really important feature of a mixture is that you're able to separate it with just physical processes like filter paper or distillation. The other really important feature of a mixture is that mixtures can have variable concentration or variable composition. You can put a little bit of salt in water or a lot of salt in water, and in both cases you'll make a solution, but they have vastly different concentrations, and there's no fixed proportion that defines a solution or a mixture like this. You know that compounds have to have a set proportion. The bonding has to suit the bonding needs of everything. So one of the ways we know solutions aren't compounds is because solutions can have varying concentration of components, whereas compounds have to have set composition of components. Then the other word in the definition of solution is homogeneous. Remember that what homogeneous means when we're just looking at things is it looks uniform to me. It looks like one stuff. But what it means is if you actually dig into the material and do all kinds of testing, it will be uniform in its concentration, or you can say in its composition, because a sample taken from one part of a homogeneous material is exactly the same as a sample taken from another part or another part. So air is a mixture, and it's usually considered a solution of a whole lot of different gases in one gas, the gas that's the main component of air. Does anybody know what the largest component of air is? There's mostly nitrogen in the air around us. That makes nitrogen the solvent gas. So the oxygen that's dissolved in the nitrogen is the solute, and so is the carbon dioxide that's dissolved in the nitrogen. So all the things that are there in smaller quantities are solutes in the thing that's there in the larger quantity, the solvent. There isn't anything inherent about a substance that makes it a solute or a solvent, and a really good example of that is dissolving ethanol in water. You can dissolve a little bit of ethanol in water and it'll make a lovely solution. You can dissolve some more ethanol in water and it'll continue to make a lovely solution. You can dissolve so much ethanol in water that you start with more ethanol than water, and then they've changed roles. All of a sudden, when you were beginning, you had a little bit of ethanol and a lot of water. The ethanol was the solute and the water was the solvent. But after a while, as you keep adding ethanol, you're going to have more ethanol than you're going to have water, and the ethanol becomes the solvent, and the water becomes the solute. When we think of solutions, people almost always think of water, and they think of things dissolving in water. But I want to say that water is not the only kind of a solvent there is, and in fact, solutions don't have to have liquids as a solvent, although that's what we almost always imagine when we're thinking of a solution. Even if you are thinking about a solution that's in the liquid state, water's not the only liquid solvent there is either. So remember, I could dissolve things in gasoline if I so desire. They just have to be nonpolar like the gasoline. But lots of different liquids can be solvents. It's just that we use water a lot, partly because it's ubiquitous in our world, and because we're water-based, and so if we're making things to go into us for one reason or another, we usually want to use the same solvent that we're primarily made out of. You can actually have solutions of metals in metals, or solids in solids. If you take a molten metal and you combine it with another molten metal, and you let them solidify, and they do solidify homogeneously. Now that's the hard part. They often sort of separate and become heterogeneous when they solidify. It's called an alloy, and if it stays uniform in composition, even when it solidifies, we call that a solution. Some alloys are true solutions. Most really are not, because when we mix the metals together, when they're molten, they become uniform in composition, but as they solidify, they sort of sort themselves out. You can get solutions of solids in solids. You can also get solutions of gases in gases. That's basically what air is. You can also get solutions of gases in liquids. An example of that would be a carbonated beverage. Carbon dioxide gas dissolved in water makes a carbonated beverage. Oxygen dissolves in water, oxygen gas, otherwise sea life that needs oxygen wouldn't be able to survive. Even though we're going to talk essentially all and only about water-based solutions, I need to make sure you remember at least once that water doesn't have to be the only solvent, and in fact the liquid state isn't the only state for solutions. All it takes to be a solution is to be a homogeneous mixture, and that can be a solid and a solid, a gas and a gas and a liquid too. When you describe an aqueous solution, so now we switch to just what comes into your mind, a water-based solution. If you're describing a water-based solution, remember that's what aqueous means. Water's the solvent. We use AQ for the symbol. One of the things that you're going to say is transparent or clear. Those two words mean exactly the same thing. Transparent or clear tells you that the stuff is mixed so well that it's not going to settle, that if there's something in there, it's so tiny I can't see it. But watch out, because the word clear does not mean has no color. When we talk about water, we say that it's clear and colorless. It has no color, no obvious color, and it's transparent. Clear means transparent. It doesn't mean colorless. What this means about water-based solutions is that those solute particles, the stuff which is dissolved, are uniformly distributed through it. That's why we don't see layers or any kind of a ripple of color or anything. It just looks like one stuff. They're incredibly small. When stuff truly dissolves in water, they dissolve as either molecules or ions. You've been writing equations like that for a while, and that's a profound statement. That's how tiny they are. That's what it needs to actually stay in solution. You can't filter them out with ordinary filter paper. Filter paper works just by having holes of a certain size. If the clumps you're trying to keep are big, they get stuck in the paper and they stay on top. If they're small, like molecules or ions, they just go right through. The holes in that paper are big enough to let a molecule or an ion go through, so it goes right on through. They don't settle out when they stand. In other words, a solution stays a solution stays a solution unless you leave the cap off, and then the solvent evaporates and you get something different. And it looks uniform, and it actually is uniform, not just looking uniform. I wanted to describe a couple of other kinds of materials to you that are similar but not solutions. So we're going to start with solution. Everything I have up here on this slide about solutions is the same as what I had on a previous slide. In a solution, the solute particles are very, very small. Ions are molecules, so we can't see them. That's why they don't settle out. That's why they can't be filtered out. And I've added something here. You can't separate them with what's called a semi-permeable membrane either. A semi-permeable membrane is something a lot fancier than filter paper, but it's the same idea. It's a membrane or a skin-like thing that has pores in it of a certain size. They're also bigger than individual molecules and individual ions, so you can't use a semi-permeable membrane to keep those in or keep them out of somewhere. Other thing, when you say transparent or clear about a solution, you're saying that it transmits light, that light will come through it. Now, sometimes the solution is so densely colored that it almost seems like you can't see through it, but if you tip it a while, you'll notice that light does come through and it doesn't bend or spread out or start to look murky, and that's what happens with solutions. They're so transparent, the molecules and ions in them are so small that light simply doesn't get bounced around. It just passes on through. What's the kind of direct opposite of a solution? It's a suspension. You've made some suspensions in lab. Suspensions have huge particles in them, clumps of particles. It doesn't mean solid necessarily particles, but big globules. And they're visible to you. You can tell, oh, that's definitely not a solution. If you leave a suspension sitting around, it settles out over time. You'll either get layers of something like oil and water, or you'll get a solid on the bottom and the water up above. You can separate a suspension with a filter. And if you can separate it with a filter, you can certainly separate it with a semi-permeable membrane. Suspensions, usually you can't see through them. Or if you do, it's all murky. The beam of light is getting spread out and bounced all around. And so if it goes through it at all, it doesn't go through it as a nice sharp beam. They're not transparent, they're not clear, they're murky or foggy. Over time, people found out there was something in between, and that's what we call a colloid. A colloid's in between a solution and a suspension. It's not quite a solution, but it's certainly not a suspension. There's actually an entire field of chemistry where all they do is study colloids. There are so many kinds and so many implications of what they do. Colloids are described as having intermediate-sized particles, generally not very big, but bigger than individual molecules. So it's either groups of ions, groups of molecules, or it can actually just be very large molecules. Body actually has a lot of colloids in it, and those colloids are created by the large molecules that are in there. Colloids are like solutions in two main ways. Particles will never settle out, and you can't filter them out. So they're small enough, even though they're groups, they're small enough that they'll go right through filter paper. However, you can separate a colloid with a semi-permeable membrane. And this is part of what your body does a lot. You have semi-permeable membranes in your body that take substances in your body and keep big molecules here and let small ones go through. That's how ions go somewhere, but a big molecule like albumin stays put. Your kidneys do a lot of this kind of semi-permeable membrane stuff. And the other thing that is kind of fun about colloids, it's kind of an easy way to distinguish them from a solution, that they scatter or widen a beam of light. Fog is considered a colloid. And if you see a light go through fog, the beam goes like this. Whereas if that light's going through transparent air, it just goes right through. So colloids will spread or scatter a beam of light. It'll usually broaden. So if you look on the side, you can see it getting bigger as it goes through. That's called the Tyndall effect. And the key feature you'll notice in each one has to do with particle size. That's the biggest determiner of where they end up.